Okay, so I guess when there's some issue in the previous lecture, I was trying to discuss what happens if we look at the mortality rate. So again, we are looking at a fully parametric model where I have pre-decided the function for my mortality rate, which as of now, let's say I assume it's Gompertz. So in that case, I know that my mu x is nothing but just bc raised to x. And now because I'm looking at the parametric models, I want to write my hazard function. So using the parametric function that I have designed for my mu. So what I'm trying to write is lambda I, which as we have discussed in proportional models, depends on t as well as zi. Then you'll have some term which precisely depends only on the t. So here by x, I mean t. So let us do some, okay, maybe we can, yeah. So this is the model that we have, all right. And now I'm trying to write this basic function. So I know that my c raised to t is the baseline hazard function, which depends only on this parameter t. And then I will have some b. So what I'm going to do is I'm going to redefine my b here as some function of zi. And that function I say is, so this is b, and what I'm going to write here is beta zi transpose. So if you guys remember, beta is like, so this is something like beta 1 x1 plus beta 2 x2 and so on and so forth, till, let's say, if I'm assuming I have p covariates, then I will have this thing up until xp. So this is the dot product that I get for this particular guy. And now if I'm saying that I'm looking at a particular individual which is denoted by I, then maybe you can, just put these particular I's here to represent that these particular covariate corresponds to the individual denoted by I. So I think it does make sense now that we know that my beta is a row vector, beta 1, beta 2, and so on till beta p, and my zi is a vector with xi1, xi2, and so on and so forth till xip. So to make this multiplication possible, I have to put a transpose here so that when I do beta zi transpose, I get precisely the way I want this thing to be. So this is what you will have in the power of e here. So here, instead of writing b, now I'm going to write e raised to beta times zi transpose. So remember whatever I have written here. So my zi and beta, these are vectors. So maybe if you want to remember that these are vectors, you can put a bar over here on the top or on the bottom as in how you feel convenient. So this is something, this is just one example of how you can write your hazard function in the case where we assume that the mortality rates parametric model is Gompertz. So now if you see what I have done here is Ct e raised to beta zi3. Okay, so now let us say I want to compare between two particular individuals. One is individual I, and let's say the other one is, so maybe what I can just do is denote my first individual as 1. So I'll have z1 upon 2. So Z, maybe I can put something like this. So if you have, let's say, 1 denotes male and 2 denotes female, and if you want to see what is the proportion of this particular hazard functions, now what you will have here is, for this particular guy, we have C raised to T, E raised to beta Z1 transpose. And for this particular individual, again, we're going to have the same baseline function. And here, instead of Z1, you will have Z2 transpose. So if you see, this baseline function cancels out conveniently, and all you are left with is the relative of this particular portion where it is only dependent on the covariates. So if you see, irrespective of any time, this lambda 1 upon lambda 2 will always remain constant. because my e raised to beta z1 and e raised to beta z2 are no ways dependent on t. So even if I change this t, the thing that was dependent on t and that could have changed this proportion is gone now. So the only thing I'm left with is something which does not depend on t. So even if I change this t, the proportion of lambda 1 upon lambda 2 is going to remain constant. And that is one of the nature of proportional hazard models. And this is how this proportionality benefits us. Now you can ignore this time variable. And irrespective of time, you will be able to figure out what makes the difference and how does it particularly affect the mortality rate of individuals. So I think the covariates will change. Here is Z1 and here I have Z2. So let us say if my X1I, XI1 represents gender, then for male and for female, I will have different values. And that is why these powers will be different. So this is how you will have your proportion of the hazards for these particular two lives, 1 and 2. And I don't know if you guys were able to see the graph that I drew yesterday, but this is precisely what is conveyed when I try to draw this graph here. So maybe we say that this is 1 and this is 2. So if you see this particular shape that it increases, takes a hump and then slopes downward, this shape is determined by how this hazard changes with respect to time. But this proportion, the difference between these two curves is only affected by the covariate, and this remains constant every single time. So if you might assume that, let's say if I'm starting a curve like this, then it should by constant it should be like this. No, because here let's say if male is taking the value 4, then a half of it will be 2. But let's say here if the male is taking the value 1, a half of it is just going to be 0.5. So the difference between 1 and 0.5 is 0.5, and the difference between 4 and 2 is 2. So you expect the difference to decrease in number as the value for this particular hazard function also decreases. But you have to keep in mind that the proportion here remains the same, because I'm seeing how my hazard function behaves with respect to time. So I hope that is clear. And this is why we have this particular name called proportional hazard models. And now if we see, there's actually one very interesting thing that happens. So again, now when we have a particular function for our hazard, what we expect is that it should be easier for us to solve and, basically figure out stuff. So now if you take a log here, so let us say we were looking at Gompertz, right? So let me just write it here again. So if I was looking at Gompertz where I have, oops, that should be B. So if I was looking at B c raised to x, which is nothing but c, let me just write this as t as well. So my lambda I is nothing but a raised to t, c raised to t, e raised to beta, zi transpose. So if I have something like this and I take logarithm on both the sides, so what I will have here is log of lambda I being equal to log of c raised to t times, so this will be plus log of e raised to beta zi transpose, right? And here for log of c raised to t, I can just take this t here, and what I'll be left with is log of c plus this log and e will cancel each other out, and what I'm left with is this. So now if you see, this particular log of lambda I function is linear in terms of time. So this again represents some convenience whenever you try to model this log hazard. So again, now what we are trying to model here is log hazard. So sometimes log gives you very convenient ways to interpret things in terms of percentages. So it is very convenient for us, because if I have a look at log of hazard, then this whole function is linear in t. So there's no t square. Here you had t in power. So this, what you can do is just regress this particular log lambda I on t, and you will get this thing as your coefficient and this thing as your intercept, let's say. So it's very easy for us to even, figure out the, basically just easy to model. But again, however easy it might be, we know that this particular parametric assumptions that we put are very, very strong. And let's say in certain contexts, there will be reasons to believe that this kind of models can be a good fit. But again, with the other options that we have available that I'm going to discuss next, there is a risk that we take of misspecifying our model completely. And what if the mortality rate is in Gomputs? So maybe, as we have already seen, Gomputs fit the middle ages and the older ages perfectly, but not the younger ages. So that might create a problem. So what we try to do is we have another tool in our toolkit, and we'll try to use that. So again, this what I'm going to discuss now was actually developed by a mathematician, David Cox, or a statistician, I don't know who he was. But yeah, he actually saw that if the proportional hazard assumption holds true, then it is actually possible for us to estimate the effect of the parameters. So when I'm talking about effect of parameters, what I mean is the direct impact of whether a person smokes or not on the mortality of that particular person. So it is quite possible to estimate the direct impact of these covariates without considering the hazard function at all. Because again, sometimes we don't care about the hazard function. All we care about is how does this particular covariate affects the kind of outcome variable that I am interested in, which in this particular case is the mortality rate. So again, covariates are just, there'll always be some characteristics of the participant that we include in our study, or let's say if you're looking at the policyholders case, there'll be the people who do try to take the policy with us as the insurance company. All right. So now if I'm talking about the next kind of model, so we will call this particular models semi-parametric models. And I'll tell you soon why. So the model wherein we fully describe the distribution of the mortality rate, that is parametric model. And now what we are going to do is we will not care about the hazard function. And so it kind of, in these particular models, then you can assume any particular distribution for the hazard function. And if you do that, then this will become a whole parametric model. But in general, we do not make any assumption because we will not care about hazard function at all. All we care about is how does the mortality changes if someone is smoking. So, and that will again be, in comparison with some baseline, and that we will see how do we define that particular baseline if we don't really care about the hazard function at all. So these kind of models are actually known as Cox proportional hazard. Yeah, so this is when David Cox was a statistician who gave away this thing. And again, so these models are actually very widely applicable, not only in actuaries, but much more widely applicable in actually medical sciences. And as you will see, I think that just speaks for itself. But again, to write the kind of function that I'm going to have here is something similar to what we saw previously. So here I'm just going to write this lambda 0t, and this is my baseline hazard. And then I will have something which denotes the relative risk associated with the covariates, which are nothing but the characteristics of the population that we try to consider. So again, this beta here is just the coefficient factor that we saw earlier. This is the covariate factor, and this is transpose. This is RE exponential, and we have these things in the power, and we have lambda 0t as the baseline hazard. So you see and you wonder what's the difference, right? So the only difference is that previously we assumed in particular that my lambda 0t is some c raised to t in case of Gompertz. Here we are not going to make that assumption. So again, at least for our cases, we aren't going to make any assumption. But again, within this Cox proportional hazard model, you can still make assumptions. So it's not going to be that if you make an assumption, it's not Cox PH anymore. It will be, but it just won't be semi-parametric. It will become a parametric model. So I guess now that we have that clarity, I don't think, I mean, have you guys studied regression before? So do you guys know how regression works? Let us say if I have to explain some random variable y using, let's say, beta 1 x1 plus beta 2 x2. So if I have to read up from this particular equation, my effect of an 1 unit increase in x1, what will that be on y? Does anyone know the answer to that? So let us say my beta 1 is 0.1. Then what do you think happens? Anyone?
I guess 1 unit change in x1 will cause 0.1 unit change in y.
Exactly right. So if you increase x1 by 1 unit, your y will increase by 10% at a particular time. So this beta 0.1 kind of helps you with that. And the similar way, it's going to happen here as well. So once we get this particular baseline hazard out of our way, which it will conveniently go, if we take proportions of any particular two individuals, then we are only left with this. But now if you see what happened here was that if you increase x1, my y will increase by 0.1, right? So y plus 0.1 is what I will get again. But here we have e raised to and then these particular things. So we'll see how do we interpret that particular kind of stuff. But again, this is going to be something like compound interest now. So if we see if we increase the values of this particular covariates z within the zi vector, then we'll see how does it affect your hazard function at the end. Okay, but maybe before we do that, let me just walk you guys through one example. Yeah, so this is what they have given to us about the ratio. So if you see this particular difference changes in absolute numbers, but the ratio of this point to that point and this to that will remain constant. Okay, so now if you're looking at the hazard, I think I just wanted to discuss this once so that you guys have some idea. Okay, so now suppose that in a Cox model, so we're in the Cox model, the covariates for the ith observed life are 56, 183, and 40 given is. So 56 here represents the age last birthday at the start of the study. So whenever we start the study, it represents what exactly is the age last birthday of this particular life. So the age, so again, this particular life could actually be of any age from 56 to 57, not 57 though. So that the age last birthday will be 56 for sure. Then the particular person's height in centimeter is 183. And then the daily dose of drug A in milligrams, which is 40 here. So these are the three covariates that we are considering. And these are the particular values that we have for this particular observation. And now we have to use the regression parameters. Okay, so here what is happening is they have already given us the regression parameters. They have given us the values of beta, but we'll see again in few minutes, how do we figure out these values of beta? Because to start off with, we only know this, this, and this. I mean, we can make people fill a form or something, and we'll know these values of the covariates. But there's no way we will know the value of these betas a priori. So we'll have to figure these parameters, values, and we'll see how to do that. But for now, they have just given this to us. And they like give us a formula for the hazard function in terms of lambda 0t. So I think once you have this given to you, you just have to multiply this with that and this with that and this with that. And raise it to E and multiply it with the baseline hazard. And that is how you will define your hazard function. If we are looking at Cox model. So once I guess that is clear, so I hope there is no doubt up until now. But this is what is very important for us. Now, again, we aren't interested in looking at hazard of one particular life. We don't sit and try to figure out the mortality rate for each of these people, but sometimes all we are interested in is the proportion. How much one is greater than the other one, or compared to other, the lesser than the other one. So again, we see that the baseline hazard will cancel each other out, and you'll be left with Z1 transpose and Z2 transpose. That makes the whole difference. And this beta vector will remain same for both of these lives, Z1 and Z2. So again, once we have this, what they have just done here is they have expanded this particular thing. So this is similar to what I did, but again, by J here, they represent the number of covariates that you have. So in this particular case, it would be something like beta 1 x11 plus beta 2 x12 plus beta 3 x13, so that you take into age, height, and the drug dose into account. So here we are assuming that we have B covariates and B coefficients for each of those covariates. And that is why you sum it up across from 1 to P, beta J x 1J. So this J is not for the individual, because here I've already defined my individual as 1 and 2. So this 1 and this 2 here represents my individual. So sometimes you might write, these as xj1, and it is just a matter of notation. So do not ever get confused, and do not ever try to fix things in your mind that whatever is in the first represents the individual and whatever is in the next represents the number of covariate. No, I mean, I think you should just be flexible about whatever notation is given to you. And once we have this, we know if I have e raised to a upon e raised to b, I can rewrite this thing as e raised to a times e raised to minus b, right? And this can again be just rewritten as e raised to a minus b. So that is the same thing that we do here. So if you see, what you will have is e raised to summation of this thing minus summation of this thing. And as we know, these betas are the constant. So you can take these betas outside and all you will have is x1j minus x2j. And this is how you will represent your ratio for the hazards of lives. Any doubt so far? Okay, so here what they are just trying to say is that the general shape that we have for this particular model, which is whether it's going to be humped or whether it's going to go something like this or whether it's going to decrease very fast, is determined by the baseline hazard. But we kind of ignore that, and that is one of the reasons why this is actually called semi-parametric model. And yeah, because we haven't yet assumed any particular thing for our baseline hazard, but we will try to figure out these parameters. Okay, so now I think this question is very, very interesting, and this will give us some good insight into how things function and how do we interpret things. Okay, so who would like to read this question for me? Savik, can you read this for me?
Yes, ma'am. An investigation is being carried out into the survival times of patients who have just undergone heart surgery at one of the three city hospitals, A, B, or C. The following data have been recorded for each patient. The force of mortality at time t is being modeled by an equation of the form. Uh, the estimated parameter values are given. Use this model to compare the force of mortality for a female patient who attended hospital A uh, with that of a female patient who attended hospital B.
Yeah, so what is it that comes to your mind first? As in, what should I be doing about? So okay, maybe you can take a minute or two to try to understand and reread the question if you want to. So what do you guys think I should do first?
We'll have to calculate lambda t for A and B, like for patient A and patient
All
B.
right. So let us try to do that. So let us first try to figure out the lambda for the female patient who attended hospital A. So female patient who attended hospital A. All right. And again, I'm just gonna write this as T just to say that this is a function of T. Okay. So what I have here is lambda 0 T. I don't know anything about this particular thing. And then I have e raised to beta zt. So I'll have e raised to beta. And now even before you expand this particular thing, what will help you is to just write the Z transpose here. So what are the values that you have here? First is that this particular person is a female. So my Z1 is going to just be 0. Then whether this person attended, so yeah, this person attended hospital A. So 0 for this and 0 for this as well. So 0 here and a 0 there. So the multiplication of this beta vector with this is just going to give you 0. So this is nothing but just lambda 0 t. So this is actually the case not only in this particular question, but this is what you will observe every single time. So if you see the way we have defined this covariates, we could have chosen a Z4, which represented, 1 if the patient attended hospital A and 0 otherwise. But we were not required to do that, and that would be redundant because we for sure know that if Z2 is 0 and if Z3 is 0, then we can conclude easily that the patient attended hospital A. So we do not need to have a dummy for that particular variable. So always remember the number of covariates that you will have or the number of dummies that you will have to create will always be one less than the number of actual categories that you observe, so that we automatically can conclude that if it takes value 0 for each of these, then this is something that we assume as the baseline group. So again, because this hazard function is just equivalent to this baseline, we call this particular group of, a female who has attended hospital A as our baseline group. So those are the people that we are going to compare everything else with. And it is always going to be the case because you will have 0 for each of these covariates, that this always boils down to just this. And you see now this G of Zi, which is your e raised to beta Zi transpose, is nothing but just 1. So that is going to be the case always for the baseline group. So here what we have is our baseline group. And if you see, that is what we are comparing against, right? So this particular thing is what we will be comparing this and this against. Okay, so now if we try to write down our lambda for the first case, what will we have? Anyone? So again, I have a female who attended hospital B. So what should I write here?
Lambda 0 t e raised to beta. So first value of covariate will be 0 for female. For attending B it will be 1, and for Z3 it will be 0.
Right. So now what we are trying to do is we actually go on to write this 0, 1 and 0, right? But maybe we can actually clearly see that this person has attended hospital B. So we intuitively, we clearly know that this Z2 is the only thing that's going to take the value 1. So we multiply this and we know that whatever we have in beta 1 and beta 3 is going to be multiplied with 0. So that's going to hold no substance. So the only thing that we will have is this particular beta 2 hat. So what you will get here is lambda 0 t e raised to minus 0.025. Does this make sense to each one of you? And now, at least for this particular first term, what you will have to do is to figure out the proportion. What you will have is lambda 0 t upon lambda 0 t e raised to minus 0.025. And this is nothing but e raised to 0.025. So this is basically what you will have. And if I write down the value of this, this is 1.0253. So whatever value I get here is actually the proportion, right? So we know there is a difference between the rate and the factor, and that is the same kind of thing that we have here. So if I have, let's say, something a upon b as 1.1, then I can rewrite this thing as a equals to 1.1b. And again, this can be rewritten as 1b plus 0.1b. And let me just erase this one for now. So what you have here is that your A is equal to B plus 0.1B. So every time, so basically if you want to see how much of this A is higher than B, assuming that B is taking a positive value, then you will know that this is nothing but 1.1 minus 1. So which is 0.1 here. So 10%. Oops, I cleared everything. Okay, all right. So let me just write the final answer for this thing was 1.0253. So the way to interpret this thing is going to be something like, so if you have the force of mortality for a female patient who attended hospital A upon the force of mortality of a female patient who attended hospital B as 1.0253, can you guys guess how much I expect the force of mortality for this A to be higher or lesser than B? So let us just say A upon B is equal to 1.0253. So what I get here is A is equal to 1B plus 0.0253B. So any change that you do in B is going to have one-to-one effect on A for sure, but there is some additional effect that it has of 0.0253 proportion. And that is how the way to estimate this particular thing is going to be. So what you will see is that the force of mortality for a female patient who attended hospital A is 2.53% higher than that of a female patient who attended hospital B. So if you know any change you do in B, and it's going to be reflected in A, but there is some additional stuff that you have here which also affects A. So we know that the force of mortality for female patient who attended hospital A is definitely higher than that for the B. And how much higher it is? It is 2.53% higher. So does this make sense to you guys? Any doubts? Okay, so what you'll do now is for the second part, you will do some similar stuff and you will get the answer. So a male patient who attended hospital C. So now if I'm looking at a male patient, I know I will not only have the beta 3, but also beta 1. So this is how you can rewrite. And again, you don't necessarily always have to write beta times Zi transpose. You can directly write these and it's valid. They won't cut your marks. Okay, so now what we saw was the whole of, the Cox model. So these are the kind of answers that we will be looking for. How much higher is the force of mortality for this particular person compared to some other particular group of people? So again, that you do by codifying the categorical variables that you have in terms of dummies. And again, if you have n categories, then you will only have n minus 1 dummy variables. So I guess that's true. Okay, so now we will have a look at how do I in actual figure out the value of beta. So again, beta is nothing but the parameters that we have. So beta 1, beta 2, and so on and so forth will be the parameters that we have specifically in the regression model. So again, this is not exactly how regression is done, but this is somewhat like the regression. So we call them regression parameters. But again, there is something that we have in the regression. So if any of you must have seen the regression function, what we have is y equals to beta 1 x1 plus beta 2 x2, yes. But there is some intercept term that we have, right? So again, whenever I try to do some regression, let's say I have some x variable here and some y variable here. So my y is explained by alpha plus beta x. So this beta here represents the slope. But whatever I start off here is my alpha, which is the cutoff here. So this is the intercept term that I always have when I'm conducting a regression analysis. So let us see if we have this thing up here as well. So let's say my lambda t comma zi will then just be lambda 0 t e raised to alpha plus beta zi transpose. And now if you see, this e raised to alpha is nothing but just a constant. So what you have is lambda 0 t e raised to alpha times e raised to beta zi transpose. So generally what happens is this e raised to alpha terms, which is nothing but just a constant, gets amalgamated in this lambda 0 t. And this, as you can clearly see, will again get cancelled off if you're trying to compare two groups. And again, you can figure out the value of this intercept as well. But I just wanted to show you guys this to kind of be able to make a reference that we are indeed looking at a regression model. It's just that we do not have an intercept, but again, we in a way have the intercept, but it just is imbibed somehow in the baseline hazard. So that is something that I wanted you guys to have a look at. Okay, but now the very first thing is, how do we determine the values of the parameters that we have? So the one technique that we have always studied is maximum likelihood method. And again, because we are looking at, the partial single parametric model, and because we don't consider the hazard function and only the covariates part, we will call this the partial likelihood. So now what we will be studying is, how do we actually figure out the estimates of the parameters for our hazard function. So yeah, this is how your partial likelihood will look like. But again, I think, okay, maybe let us just try to see this first. So what we have here is our likelihood function, and the parameter is the whole beta vector, which will be consisting of beta 1, beta 2 up until beta p. If I assume that I have p covariates, okay, but there are some subtleties that we see here. So we see that if so again, what are the times that I will be interested in to figure out the likelihood for? So let us say I assume that I observe k number of deaths. So k is nothing but the number of deaths that I observe. And again, I'm noting my time as j here. So when I'm writing my RTJ, that just denotes the set of lives which are at risk just before you observe some particular person to be dead. So again, this j will only go from 1 to k, because k is the maximum number of people I observe being dead here. And every time we have a person dead, we will try to figure out the mortality rate. We'll have to see what goes in the denominator, right? And that is the number of lives that were exposed to the risk of being dead at that point in time. And for that particular thing, you have this thing in the denominator. So here, this is only corresponding to the jth life, which died. And the thing that we have in the denominator depends again. So that is just summing up across all the lives that are exposed to the risk of being dead. So if you see, there's a subtle difference. In the numerator, we have j. In the denominator, we have I, and I belongs to all of the lives that are at risk. So we sum up the covariates of all of those things, because that is what matters in the case of the hazard function, right? The baseline and the intercept is just going to cancel out each other. Can you guys hear me? I know you guys can't see the screen, but am I audible?
Yes, ma'am.
Okay. So we'll just wait for the internet to come back. Yeah. So what I was trying to say is in the denominator, what we have here is summation over, again, all the lives that are exposed to the risk of being dead at that particular point in time, which is TJ. So this is what we have. And maybe so the next thing that I was trying to say is that this denominator actually, I mean, again, not only the denominator, if you look at the numerator as well, this likelihood does not at all depend on time. The t variable does not appear anywhere in the likelihood function. And whatever we have in the denominator only depends on the order in which people fail. Because all we care about is not the precise time at which this particular person died, but all we want to know is how many people were alive by the time this person was dead, or at the time when this particular person was declared dead. So we want this particular thing to be, again, consistent. So again, in the next chapter, we will see what happens if, let's say, to record deaths, we are looking at age last birthday, and if to record the exposure, we are looking at age next birthday. So then there will be some adjustments that we'll have to make, but we'll look at that in the next chapter, which is in the evening today. But again, so this is what I wanted to convey now. And let us try to have a look at this particular example. Okay, so here we have a group of 6 lives. So these are the number of observations that we have, 6, over a period of time as part of a mortality investigation. Each of the lives was under observation at all ages from age 55 until they died or were censored. So we observed lives from age 55 up until they either died or they left the observation or we lost the follow-up or something else. So we have the ages, we have the age of exit of each of these particular people and the reason for exit. So some of them died and some of them got censored. And we have the gender of each of these particular people. Okay, so now let's see what we have to do. So the following model have been suggested for the force of mortality. Yeah, so again, don't be bogged down with the notation. Okay, we studied lambda, but here I have a mu, that's fine. So this mu here is just nothing but the baseline hazard, which is mu 0x and e raised to beta z. And again, there is only one covariate here, which is the gender. So this z takes value 0 for a male guy and 1 for a female person. And again, x denotes the age factor. And now what we have to do is we have to write down the partial likelihood for these observations using the model above. So again, the way we go to solve for this particular thing, so we'll see the contribution of each of the lives that was dead. So first of all, we see how many lives were dead. So this is the first, second, and third. So we have to figure out the likelihood of at these 3 points in time. And again, when we look at this, we know each one of these 6 lives was alive when the first life died. But when we look at the third life, we know that the first and the second one was dead. But is this how we are going to look at it? No, we have to look at the age of exit, right? Because what we know is when we started the observation, we started with, the age 55. So people aged 55. And again, I mean, here for our convenience, the ages at exit are actually, so again, it doesn't really matter much about the age of exit, but this will help you in a way to figure out this particular X. But again, what you'll have to see is what is the age of these 2, 3, 4, 5, 6 person when this one person died. So when this one guy was aged 56, what do you guys think was the age of 2, 3, 4, 5, and 6? Will it be same as 56 or will it be different as 56? What do we expect their age to be? Anyone? So again, whenever I'm trying to figure out my partial likelihood function for the death of my first observation, I know that the very youngest death I have observed. So again, I mean, the age at exit is in a nice orderly fashion here. But if let's say the third observation and the first observation were exchanged, then you will not consider the third observation. In the second case, you will have to consider the person who died, young as the very first thing that happened to you. So what might help us is, let's say if we draw a number line. So again, we have 55 here, 56, 57, 58, 59, 60, 61, 62, 63, and so on and so forth. That's it. Right. So this particular guy died at the age of 56. Then this particular person got censored at the age of 62 and died at 63. And then whatever happens next, right? So again, what we know is that when we started our observation, everyone was aged at 55. So we know for sure that when I was here, each of these lives were aged at 55. And when 56, so when each of these lives progressed to being aged at 56, this particular one life died. So we'll try to figure out this thing, and we know none of these lives died before. So the number of people we have exposed to the risk of being dead was all of these people, which is 6, right? And that is the reason why, if you now try to figure out the contribution to the partial likelihood for the death of this particular person, you will see mu156 upon mu1 till mu6 to take into account all the 6 people. But again, for this X here, age, you have 56 everywhere. And why is that the case? Because I know that I start observing people at 55. So when this particular person died age at 56, I know for sure that the rest of the lives were also age at 56. And that is the reason why we have mu156 upon the summation of summation of the respective mu's for the people who were alive at that point in time. Does this make sense to you guys? So the next thing that we will do is we'll just expand this mortality. So here the force of mortality is expanded in such a manner, and that is what you will do here. So you have mu056, but again, the thing that we know for the person who died here is that this particular person was a male. So we see that the covariate is just 0 for male, and that is why this e raised to beta z is going to just be 1. And that is why you don't see any e raised to stuff here. So this is all you will have. So in the denominator, all you will have is the summation of So for the numerator, we don't see any e raised to come here. But again, when in the denominator, I try to add all the people's force of mortality, I see that some of them are male, but some of them are female as well. So we have e raised to beta, and no e raised to beta stuff here. So we know that, again, we have seen that these two are the females and other ones are male. So always remember, this is how you will try to figure out the contribution. And again, if you take 056 as common from the denominator, it will just cancel out, and all you will be left with is 1, 2, 3, 4, which is 4 plus e raised to beta and e raised to beta. So 4 plus 2 e raised to beta. And in the similar fashion, we will determine the contribution of the second death. So if we have a look at our question, the second death happened at the age of 63. So we know that the number of people alive at that point in time were only 4 people, right? So this particular person died and this particular person got censored. So we don't take these two into account. So we'll have 1 e raised to beta and then 3 plus e raised to beta basically in the denominator. And that is what you see here. And again, e raised to beta in the numerator. To just take into account the fact that the person who died was female. And similarly, you will figure out the contribution for the third death. And as we know, to figure out the whole likelihood, and again, we just assume that these deaths happen independently of each other. And that is why you can just multiply them together. And this is what you will get for your partial likelihood function. So does this make sense? And again, I think you might just wonder, why have we written C here? And we have this particular thing and this particular thing getting multiplied. But if you have a look, this e raised to beta is here as it is. And herein they have taken the 2 outside as common. And that is why you're left with e raised to beta plus 2 here and e raised to beta plus 3 is as it is. But again, the 2 that you take out as common here and that will render you 1 upon 6 something here, that is vanished. Because again, when we try to take log likelihood and we try to differentiate this with respect to the parameter, that is not going to matter at all. So you just write it as C here, which is some constant that you do not know. So now this C here not only takes into account the constant numbers that we have here, but also takes into account the baseline hazard. But again, as we know, I mean, the baseline hazard actually just got cancelled here. So this constant is just basically going to be 1 upon 6 for this case. But again, you can ignore that. At least if you don't care about the actual value of the likelihood function. Okay, so as we have discussed, now we will try to maximize this particular likelihood function to just say the data that we have observed is much more likely to be observed in for what values of the parameters. So to figure that out, we will again, so we are starting off with this and we will look at the log likelihood. So as we expected, this log C plus beta, because log of e raised to beta is just going to be beta itself. And then you have the rest of the stuff. So this comes from the denominator. That is my minus and the minus here. So this is what we have. And then you will differentiate this with respect to the parameter of interest, which is my beta here. Okay, so one question might be that, okay, so beta here is not only, one particular number. Beta here now is a whole vector that we are trying to differentiate something with. So for the first differentiation, it doesn't quite matter. But whenever we are looking at, the covariance matrix or something else, then we'll have something that we'll see again. So I don't want to say it now, but it is actually called information matrix because it provides us information about the covariates. And it's also called covariance matrix, that matter. All right. So now what we do is we differentiate this particular log likelihood with respect to beta. And this is what you get. And then you equate this particular thing to 0. You do some algebra, blah, blah, blah. And this is the value for beta that you derive at the end. So again, I think again, so you all might question, this beta should have been a vector. So why is this a number here? Because we only looked at one covariate, right? So we only had one beta in this particular case. And that is why this is very straightforward. So this beta was just going to take one value, as we only have one covariate, which is 0 for male and 1 for female. So this is the value of coefficient that you will have. And again, to just determine whether this was indeed the maximum or not. So again, you can just differentiate this thing again with respect to beta. But again, this is why, because we are assuming that, because we know that beta is not a vector, it is just one particular parameter that we are looking at for this particular case. So I hope this makes sense. And if you do this, you kind of prove that yes, it is indeed less than 0. So indeed we are maximizing, not minimizing at all. So this beta hat's estimate is nothing but 1 by 2 log of C, which is 0.896. Any doubts so far? Okay, so this was very easy for us, right? But in general, whenever things happen, it might be a bit complicated. So the analysis that we just did, we made actually a very, very strong assumption. We assumed that for the moment, so we are assuming that there is only one death at each observed lifetime. So we did not take into account the probability that there can be a possibility that two people die at the same time. So if we have that, what will happen? So let us try to expand our model, expand the example that we saw, and add these particular two lives to it. So again, here we aren't assuming that there is someone who dies, but if you see the age at exit is 56, and the reason for exit is censored for life 7, which is again, categorized in the male category. So if you see now at the age of 56, we do not only observe death. So just to go back, if you see the very first death, the death that we observed was of a male age at 56, right? But again, here we see that another male age at 56 gets censored. So how are we going to treat this? So the way we will treat this is again similar to the assumption that we made in the previous chapter, which is that if a death and censoring happens at the same time, you assume that censoring happens next and the death happens first. So the only thing that's going to change is how many lives you have exposed to risk at that point in time. So if you're observing 8 people, again, there's only 1 female added and 1 male added. So instead of 4, you have a 5 here, and instead of 2 e raised to beta, you have a 3 e raised to beta here. So that is the only thing that will change. So I guess this is one kind of a complication that we can have. But again, there are other kinds of complications that we can see. And that could be something like, so maybe we'll just try to have a look at the example again here. So let us say I have this particular thing given to me now. So this is some example that I have. Isha, can you read this for me? Okay, Vanshita, can you read this for me?
Yeah, sure.
Just to hold your mic a bit closer.
Now is it fine?
Yeah, perfect.
The investigation was carried out into the survival times measured in months of patients in hospital following liver transplants. The covariates are one I equal to 0 for placebo, 1 for treatment X, and Z2I equal to weight of patient measured in kg. The observed lifetime with weights in brackets were as follows. Observation with an asterisk represents censored observation.
Yeah, that's it.
Okay.
Yeah, okay, we haven't studied the assumption that they're going to ask us to assume. Okay, so now the thing that we see in this particular example is that, so we have 2 covariates, not only 1 covariate anymore. The very first covariate represents whether the patient was actually given some treatment, or so for those who might not know what placebo is, it is something like giving a patient actually nothing, but just a dose of some vitamin and saying them, okay, this might cure your headache. So the thing that you give them is actually of no particular use for the headache, but they might think that yes, the doctor has prescribed me the medicine, so it might just be a psychological factor that the doctor prescribed you the medicine that and your headache is now discontinued. So placebo is just to take that into account, where you So again, I don't know if you guys know this, but whenever this kind of trials happen, people generally do not get to know whether they were given a placebo or whether they were given actual medicine whose effect we want to see. So let's say if there is a particular group of patients who have headache, and we are trying to see how effective is the medicine that we have developed to cure the headache. What you will do is you will set aside, you will divide your population into two. So only the researcher will know which one of these people belong in what category. And one category will be known as the control group, and the other category will be known as the treatment group. So when I say control, that will be the ones who will be given fake medicine, and the treatment group will be given the actual medicine. So that when we are actually trying to see the effectiveness of this medicine to cure a headache, we do not compare it with people who didn't have headache at all. We'll have to compare the effectiveness of this medicine for we assume that everyone has the headache, and for the people who were given the medicine and the people who were not given the medicine. And that is how you will try to actually estimate the actual effect of the treatment that you are trying to give to the patients. Okay, so now again here, if I see in the brackets, I guess that is the weight of each of these patients, and 3, 6, and that is the time. Yeah, so 3, 6, 9, 11 represents the months that have been passed for this particular people under the investigation. So if I see, we have 3 observations that have passed 14 months under our investigation. Okay, and we see one person is aged 75, other one is 68, and the other one is 49. And that person actually gets censored at time 14, right? So now if we see, these are the lifetimes of people, right? So at the time 14, so after 14 months into the investigation, we see that 2 people die at the same time, right? So how will we take this particular thing into account? So what we see, the first assumption that we make is that the deaths of these 2 particular people, one aged 75 and the other one aged 68, is independent of each other. So I think, as you all might have guessed, we will just take the likelihood of 75% and then we'll take the likelihood of the 68% and we'll multiply them together. But now the question remains, what happens to the lives that I assume to be exposed to the risk? Both of these people died at the same time. But when I'm multiplying them, next, when I'm not taking them into account together, and trying to multiply them, and by assuming that one dies after the next, there's something fishy that's going on here. So again, there are various ways in which you can make some approximations that will help you to figure this thing out. And one of them is Breslau's assumption. So this is what we are given here. And this formula looks a bit complicated, but again, you have this SJT here, which is, nothing much more than just the sum of the covariates. So again, I think we'll come back to this particular formula once we solve this question to understand it even better. Okay, so now when I'm talking about this particular question, it is asking me to determine the contribution to the partial likelihood that is made by the deaths at time 14. So again, I know that there is an observation that got censored at the age of 14, but I'm not going to consider this thing. I will not consider this thing as censored before the death. So I'm going to count this particular person when I'm talking about, the likelihood and basically determining the lives that are exposed to risk by the time 14 from the start of the investigation period. But now if you see this person, this person, this person, and this person, so these 4 people died even before we see the light into 14 months of the investigation. So again, the thing that you were going to have in the denominator where you figure out the exposed category is only these 4 people, right? So what you do is you write down the hazard function for each of these 4 people. And for the numerator, you see 2 people died at the same time, right? And again, some of them were given placebo and some of them were given a treatment X. So now considering that in and considering this stuff, so all of these people were given placebo and all of these people were given the treatment. So for these and these 2 people, you will have to consider in the placebo, which takes a value 0. So the only thing that you're going to have in the hazard function is the weight, which is here. So, and for the next guy, so this guy who dies again at the time 14 from the start of investigation was given the treatment. So here, if you see, we have beta 1 here and 1 for the treatment, which they haven't written. So now we know this is the lives that were exposed to risk when this person died. And when I'm talking about Bresler's assumption, I assume that this remains the same for this guy as well as this guy. So they both die at the same time, which is why you assume that the exposed to risk category of people stays the same for this as well as this. So what you will do is to figure out their contribution to the partial likelihood. This is for the first person dying, and this is for the second person dying. And as we know, the denominator is just the same. This gets squared, and these two get multiplied in the numerator. And now, because we are multiplying this and this, and again, this you'll have 2 of these baseline hazards, and because we have a square here, you might just feel convenient to take this mu014 outside as common and square that, and this will cancel each other out, and you'll be left with this thing. So you see, what happened here is the summation of the covariates of this person who died and this person who died. So this is the same thing that my Breslow assumption is trying to say here. Okay, so I see the sharing is gone again. Can you guys hear me? Yeah. So this is what your Breslow assumption actually says. So they're saying here that this particular Sj that we have now with the beta here is the sum of the covariate vectors Z of the di lives observed to die at time t I. I think that's a J. So yeah, dj and tj. So this is what they mean by this particular assumption. So there is another alternative method actually that goes by the name of Efron's method. But yeah, this Breslow guy came up with this approximation first, and this is what is actually widely used. So this is how you will figure out the actual contribution of this particular lives being dead by time 14 from the start of investigation. All right. Okay, so now next up. So this was the case where we saw that my baseline hazard, okay, so fine, with my hazard function, I have 2 covariates now, right? My first covariate is the weight of the person. I'm sorry, my first covariate is the placebo or the treatment, and my second covariate is the weight of the person. So how do I go about actually differentiating this and trying to maximize the partial likelihood? So if we see here, my beta is now no more a particular value. My beta is now a vector. So now when I try to differentiate this particular log likelihood with respect to a vector, what do I get? So there are some rules when we try to multiply matrices. Okay, and now I have assumed that my beta is a row vector, right? My beta is 1 by p vector. So I have p number of terms and I have a row. So this u beta here now represents the first derivative that we usually take and equate it to 0 to figure out the value of beta. So now what you will do is you will just write this mu of beta, and again this beta is a vector that you write here, which comprises of beta 1 and up until beta p. So again, if this beta were a column matrix instead of 1 by p, if this were p by 1, then this u of beta would be something like this with the same elements in here. But because my beta is a row vector, you are bound to write this particular thing in a row. And this is known as efficient score function. So again, these are just the terminologies that are getting changed, but we are trying to do the same thing. We differentiate it once and we equate this particular vector to 0. So what we will equate this is to 0, 0, 0, 0 p times, right? So each of these particular values should be 0. So you will get the precise value for each of these betas that does maximize the partial likelihood that we're looking at. So again, you might again also think that all of these methods that we studied, basically differentiation and then the maximizing of the likelihood, this works with the likelihood, right? Not with the partial likelihood. But again, I mean, we're kind of assuming that this partial likelihood behaves much like a full likelihood. So asymptotically, it doesn't matter. So when I'm talking about asymptotically, I assume that I have a large enough sample. So this is my first derivative, and this is how it's going to look like, and the estimates that you will have for beta hat. So my beta hat again, this beta here represents a vector. So this whole beta hat and the elements of this beta hat will be beta 1 hat, beta 2 hat, and beta 3 hat, and so on till beta p hat. So that is how you will derive the values for the estimates of these betas, which are the parameters. Okay, but once we have done that, now what do we do? So again, we have actually, seen this particular case. This is not the first time we are trying to see this thing. We have, when we were trying to figure out the MLE for normal distribution, we saw two parameters. We had a mu and a sigma. But what we did was we first differentiated with respect to mu, then with respect to sigma, and we solved each of them simultaneously, right? But now as we have these many parameters, p parameters, it will just be difficult to do that. So we try to be efficient in the way we are going to write that. And that is why I'm using a vector notation now. So we have this. But again, now what about the second derivative? So what happens with the second derivative is that we have something known as information matrix that gets created. So again, the name is just very complicated, but this is what you will ideally get. So again, this might look a bit complicated and you don't necessarily have to remember all of these because it's very easy. So if you write beta 1 here, beta 2 here, and so on till beta p here, and then you write beta 1, beta 2 till beta p, every time in the numerator you have the log likelihood as it is. And the two parameters that you differentiate this with. So again, we know we have to differentiate this thing twice to see whether indeed we are maximizing or minimizing. So what you will have here is this beta 1 and this beta 1. This beta 2 and this beta 1, this beta p and this beta 1. So first you put in the row and then you put in the column. First you put in the row and then you put in the column. And that is what you do everywhere. And again, we have to analyze this thing at the estimates that we have derived when we equated this particular thing to 0. So this matrix is actually known as information matrix. And the variance, as we know, is not precisely this. So the Kramer-Rao lower bound actually said to us, what we have is this double derivative minus and its inverse. So this is the same kind of thing that you're going to do this and do to the whole matrix now. So the whole matrix will get multiplied by a minus sign and you put an inverse over there. But again, what you will have to remember is that the inverse of 3 is 1 upon 3. But inverse of a matrix has a particular formula that you will have to figure out that will help you to figure out its inverse. So again, this is the same thing. So this is precisely for one parameter case. And if you have more than one parameters, then this is what you will have. So if you have p parameters, the matrix that you get for the variance is p by p matrix. And remember, you have a minus here and an inverse here. But this matrix is known as information matrix, which is denoted by I beta. And again, you just have I representing, small I representing the row number and small j representing the column number, which is why you have this differentiation with respect to beta I and then beta j. So I hope that's clear. And this is basically what you have. So again, this was just the one parameter. No, so I guess, yeah, this was one parameter case. So you just double differentiate it and you see what happens. So again, the beta value that you got was a half of log of 6. So this is what we have for the value of beta. But again, as we have just seen, a way to figure out the variance and everything else, we can actually create a confidence interval around this beta. And we'll see whether the value of this beta is 0 or not. Because if the value of beta is 0, then we know that any change in that particular covariate does not affect the force of mortality. So I can exclude that covariate from the model that I'm considering. So we have to check whether 0 lies in the confidence interval for this beta guy or not. Because if it does, then there's a good chance that the value of beta will be 0 itself. And that will render your covariate to be insignificant to the outcome variable that we care about, which is again the force of mortality in this case. So what you will just do is this variance. So you do this. So again, you have ignored the minus of this thing inverse, and this is what you get at as the answer. So what we have done is we have evaluated this particular variance at the beta hat value that we derived. So this is a half of square root of 6. So not, it was half of log of 6, which if you have in the power of e, comes out to be square root of 6. So again, this is the variance that you have. So the standard deviation will be this. And again, if you're looking at the 95% confidence interval, you will just do the same thing that we always do, and you get this as the interval. So if you see, 0 does belong to the interval, right? So there is a good chance that the value of my beta hat is just 0. So if the value of my beta hat is 0, then I know that it is in no way affecting the outcome variable. Force of mortality is not affected by the beta, I guess. I don't remember. Wait. What was the beta? Yeah, the beta measured the gender, right? So it took a value 0 and 1 corresponding to being male or female. So now what you can conclude is that the age, the force of mortality does not depend or does not vary with a person's gender, because the beta for the gender variable is likely to take up a value of 0. So that is how you figure out whether a particular covariate that you're looking at is significant or not, whether it is important or not to explain the force of mortality. But again, sometimes you only want to care about one particular covariate. But let's say now if we have, let's say, p number of covariates, and I think that maybe something else might also explain this force of mortality. So I try to add more and more covariates. But then there's an issue, when should I stop? Because I can gather as much information as I can possibly, right, from people, and that will allow me to figure out a precise way to the force of mortality. But again, as we know that the information is costly, right? And generally people, when they're trying to take out an insurance policy or something, many people try to sell their policies by saying that the firm that they are going to give you is gonna not cost you a lot of time. So sometimes if you're trying to ask for way too many details, people might be reluctant to take the policy. So there is a trade-off that you have. But again, now if we see what kind of covariates should we include and what kind of covariates should we not include. So whether a person has a car or not, does that matter? Does that affect the force of mortality of that person? We'll check. And if it And if we figure out that it does, then we'll ask them this question, right? But again, this is theoretical. So this is another test that we can do to figure out whether the covariates that we add, additional covariates, do they affect, are they significant? Do they actually impact the force of mortality or not? So the test that we are going to do to figure out the same is called likelihood ratio test. And I think you all might have seen this as well in your CS1. So here I have two models. One is the model with P covariates, and the other one is the model with the same P covariates plus some additional number of covariates. So that additional number of covariates I denote as Q. So I have one model. So I have one model with P covariates and another model with P plus Q covariates. So if we see here, we have this likelihood ratio test whose test statistic uses the log likelihood. So again here, don't look at this, you should look at this. So they have only written L, but I mean, they mean log L. So what we look at is the difference between the log likelihood of these two kinds of model that we create using a subset of covariates that is common in between these two. So P number of covariates are common. So what we are trying to say is the additional Q covariates that we add, do they matter or not? So obviously our null hypothesis, we assume that these do not matter, which is why we equate the coefficients of this beta P plus 1 till beta P plus Q to be 0. And now we want to see whether these are indeed 0 or not. So if we figure out that we kind of reject the null hypothesis, then we will say that yes, the additional Q covariates that we add they are significant. So they are actually, efficient in determining the force of mortality. So again, we will try to do the same thing. And the very reason we have this -2 being multiplied, so minus is just a necessity, and this 2 here actually is for this particular test statistic to follow a chi-square distribution. And again, as we know, we'll have a look at the upper tail chi-square distribution to figure out the significance at the percent that we decide a priori. So I think, do we have example? Okay. So I think we have an example. I don't know. I think we might have an example at the end of the chapter questions. But yeah, so the minus that we have here will always render this particular test statistic to be positive in number. And that too will help us to just compare this thing with the chi-square. So again, you can add some covariates. You can add some more covariates and check whether those actually impact your force of mortality or not. Okay, so the next thing that they're trying to check here is what happens if I have some more covariates that aren't indeed, any different covariates. So sometimes you might, so let us look at this example, right? So we have 1, 2, 3, 4, and 5 covariates. And my first covariate represents the socio-economic group, where 0 represents lower and 4 represents a higher. And Z2 is just the sex, so 0 for male and 1 for female. Z3 represents smoking status. And Z4, here if you see, this is some multiplication of Z1 and Z2. So what does that take into consideration? Would anyone want to guess what's happening here? Anyone? So what's happening here is basically sometimes you might think that there is some association between the mortality of people who come from a particular socio-economic group and a particular gender. So to check that, what we do is we create another covariate, which is the interaction between these two variables. So for Z4, we have an interaction between the socioeconomic group and the gender. And for Z5, we have an interaction between the socioeconomic group and the smoking status. So we sometimes feel that the force of mortality will be different for people who come from a particular socioeconomic background and smoke. So we think there might be some additional effect, some additional impact that this particular interaction might have. So to check our hypothesis, we will use hypothesis testing. So my null says that my beta 4 and beta 5 is 0. It means that there is no interaction. And then you will test against it. So what you will do is you will create one model with only this Z1, Z2, and Z3. And the other model, you will have 1, 2, 3, 4, 5. So that you can figure out a likelihood ratio statistic, which will be minus 2 log of L3 minus log of L5. And then you compare this with the chi-square distribution. So again, whenever we're looking at chi-square distribution, we have to figure out the degrees of freedom, right? And the degrees of freedom will be the difference between the covariates here. So we have P plus Q minus P. So Q. So you will compare this thing with the chi-square with degrees of freedom Q. So this is how you will try to figure out whether you should include some covariates or not. So if this turns out, I mean, if you fail to reject H0, then you know that this and this do not matter at all. So the next thing that we'll try to do is, so now once we know which kind of, how do we determine whether a particular covariate is significant or not, the last thing that a modeler has to do is now prepare the whole model, right? You will have to build the whole model. So there are two different ways in which you can build the model using this criteria. So one is, what you can do is you start with nothing. You say that none of these covariates impact the force of mortality. And then you can try to add more and more covariates and check the significance of each of them. And if it is significant, you add them. If it is not, you ignore that covariate. So that is one method that you can do. And again, generally, this method is used by adding first the covariate that you think has a much more significant impact. So sometimes what might happen is, let's say you have age, you have smoking status, and you have whether this person has a car or not, and the socioeconomic background. So you see that if you test for socioeconomic background, it will become, let's say it comes as a significant. And if you test as whether this person has a car or not, and that also comes out as a significant covariate. But if you include socioeconomic background and having a car or not simultaneously, so by simultaneously, I don't mean by interacting them together. I just mean if we have a model where my Z1 is socioeconomic, Z2 is car, then you might see that once we've included the socioeconomic status, the car variable doesn't add much to the model. So sometimes what you do is you first regress it on all of the covariates that you have information about, and then you try to eliminate the ones that have no significant effect. So once you have already taken into account the socioeconomic status, you might see that the car variable now does not hold any substance. So it's not significant anymore. So you will eliminate that particular covariate. So that is another way you can build a particular model. So one is you start off with nothing and you go on to add more and more. And the other is you start off with a full plate and you remove the ones that you don't think are necessary. So again, these are just two different ways in which you can build a particular model. And I guess that is all about this particular chapter. So again, what we did was we studied particular ways in which I can model the hazard function. And then at the end, I sometimes not care about the hazard function. So all I want to know is how much smoking affects the force of mortality for this particular person. And to check that, I studied my Cox proportional hazard model. And then we saw how do we actually go on to prepare a model which will work well with the data that we are given. So this is what you will do once you have some data. And then the next time whenever you collect data, you will just fit that data into the model, assuming that whatever has happened in the past does reflect what is going to happen in the future, at least if not precisely, but approximately. Then you will be able to figure out the force of mortality of the people. But again, I see that, nowadays, the trends are really changing very fast. And this is a very difficult task. So I have seen that whenever people apply for jobs, there are actually teams in companies that are just dedicated to preparing a theoretical model that the other people in the company will use later on to model and stuff. So that's, if someone is very much interested in, the theory of this is actually very, very interesting. So once you have this, once you have the results of the model, this will in a way allow an insurance company to figure out what kind of premium you should charge to a particular person. And yeah, if you're looking at the placebo treatment, it will actually dictate whether the particular treatment is effective or not. So this is why this Cox proportional hazard is actually much more applicable in biological statistics. And yeah, I think so. All these examples of genes, chromosomes, and this cancer research, people try new drugs with the coronavirus as well. We have to conduct the trials for the vaccination, which one works, which one does not. I think I was hearing it in the news that the Covaxin in India, they were supposed to have trials, and this was very sad to hear. But what they did was they actually didn't tell people that they were not being vaccinated, but they were actually partaking in a trial to check whether the vaccination was helpful or not. So most of the people didn't know that they were taking part in a trial. So ideally that should not happen. People should know whether they are included in a trial or whether this is an actual vaccination drive. So most of the people taking part thought that this is the actual vaccination drive, and they took vaccines. But what was actually happening was they were the subjects of a trial which is going on. And the hospital was actually supposed to call up people and take regular updates, whether they have a fever or not, whether they have developed some other symptoms or not, whether they feel a relief or not. And that wasn't done as well. And so, yeah, I guess, this is just sad. But yeah, that is where these techniques that we have studied actually come into use. So this is very, very practical. Okay, and I think maybe we can try to do some sums. Okay, I think we have some time. So what we can do is we can try the sums itself. Okay, so we'll try this particular sum. I want you all to read this and basically try to figure out what is it to be done and how can we do that. So here they have not defined the covariates. Well, the very first question is define clearly all the terms you use and write down the expression for the hazard function in the model. So just read the question and then you guys can tell me how should I go about solving for this question. Have you guys read the question yet? Are you guys already solving it? Can you guys hear me? Hello, am I audible?
Yes.
So have you guys read the question yet? Or no? So what is it that we have to do here? Who will explain me what are we asked to do here? Oh, Mashida, I cannot hear you.
Hello.
Yeah, now I can. Go on.
We have to write the hazard function, which is lambda x like zi. We have to specify all the variables.
Okay, I cannot understand what you're saying, Mashida. Can you speak up a bit louder?
We have to write the hazard function
Yes.
zi, and we have to mention all the like z i's that we are using. Like we have to specify what.
Yeah. Okay. So what is it that you think I should do now? Should we first specify this ZIs? How many covariates do you think we are going to have here?
It will be one less than that category.
Right. So it will be one less than the categories. And so what do you think we are going to have here? So we see that each of this person can either belong to a large employer or a small employer, or they could have studied any of these 4 degrees, or they could have been living in any of these 3 locations, right? So what we can do is we can define a basic person for whom the value is 0, right? So remember, whenever I'm looking at a baseline group, I know that the value of the covariate term for that particular group should be 0, right? So if we see the parameter is 0 for this, 0 for this, and 0 for this. So maybe we can say that the person whose employer is a large company and who has a degree in none of these 3 and is from London is our baseline group, right? So we can exclude these 3, and for the rest of the stuff, we can define my Zs. Does this make sense to you guys? Does this make sense?
Can you say about the baseline? What is the again?
Okay, so whenever I'm talking about my hazard function, which is something like this, right? For let's say person I have lambda 0t e raised to beta zi transpose. So this is what I have for my hazard function, right? And now whenever I'm talking about the baseline group, I want this term to be 1 for them. So for this thing to be 1, I want whatever is there in the power to become 0 always, right? Because whenever I'm talking about the basic group, they do not have, so let's say the placebo and I mean the female category, if you were looking at the previous cases. So I want my power to be 0, and either this covariates themselves should take the value 0, or this parameters should take the value 0. So here they have given us the values of the parameters. So by parameters, they mean each of the betas corresponding to each of these covariates. So again, what I'm doing is, if I know a person is not in the small company, then I can easily conclude that the person is in the large company, right? So all I need is to create one covariate for the small. And if the value for that is 0, then I know that this person was working in a large company, right? And similar thing for the degree study. I can create one covariate for this, one covariate for this, and one covariate for this. And if my covariate value for all of these three is 0, I will clearly know that this person has studied some other degree. And with same with the location as well. But now whenever we are trying to define something, I mean, none of these things happening, which concludes that whatever we assume for the baseline group has happened, that is what will render this particular power to be 0. And that is why, because you have, that is why you call it the baseline group, because all that matters is the baseline hazard. So this is where you see no impact. So this is your base, which from which you will compare the other people. So again, what you want to see here is, let us say you have two particular people. One person has a science degree and has worked in a small company, and other person has a arts degree and has worked in a large company. How will you compare these two people? So this is what is going to help you. But again, sometimes what will help you is coming back to the vaccine example that I give you guys, to check the efficacy of a vaccine, what do I need? I need all of my people to have the disease, right? So that then I can see whether the treatment is effective or not. So my baseline group here will consist of the people who have the disease, right? And then I will give some of them the vaccine and some of them I will give the placebo. Then I compare against. So what I'm comparing against is the placebo group, right? Where they were given a fake medicine. So I'm comparing my other people who got treated with the actual vaccine with the people who had the headache but were given a placebo. So here what you will try to do is, let's say you want to compare what happens once you graduate. So if you, let's say, graduate with a science degree, what is your force of mortality if you work in a small company or if you work in a large company? So ideally, you would want to question whether there is a significant difference between these or not. So whenever you try to figure out these differences or whenever you try to compare two things, you need to set up a base. So again, you could do it in any other manner as well. It doesn't really matter much. So you could assume large, you could assume small, and you could assume science, and you could assume overseas as your base. But again, just because the parameters are 0, so this is convenient for us. And that is the reason we actually do this. So if the parameters were not given to you, then you could take any one that you wish to be, base from this, and this. But because the parameter is given and this is 0, it does show us that this is the base that we're looking at. Because this is what will render this particular thing to be 0 and this thing to be just equal to the baseline hazard. Does this make sense, Vanshita?
Yes.
Okay, good. So now in the first question, what we want to do is, we want to just define the covariates, right? So once we have determined that this, and this are going to be our base, we don't need to define a covariate for large, other, and London. So we'll define one covariate, let's say Z1, which takes a value 1 if you are small, and 0 if not. Then you can have Z2 if it takes a value none, it's going to be 1. Z3 if the person has studied science, it's going to take a value 1. Z4 1, Z5 1, Z6 1. So you will have 6 covariates, and each of these with these respective parameters here. So maybe we can go back here to see. Yeah. So if we have a look here, yes. So what they've done is they've defined this hazard function in terms of baseline hazard and then all the covariates. Yes, still, so we have 6 number of covariates, and each of these you have in here with the corresponding value of beta that we have. So if you see, if you put something with a 0 value of beta here, that covariate would automatically be, discarded. So let us say if instead of considering small as the covariate, let's say if instead of considering large as the covariate, if you would have considered small as a base covariate, then my Z1 will take a value of 1 if the person is from a large company and 0 if not, right? But my beta for the large is 0. So this Z1 will just not show up in the equation at all. So I will not know whether the person is from a large company or a small company if my ZI doesn't show up in the equation, right? And that is why once you're given that the parameters are 0, you will take those as your base category. So that is how you will define your covariates. Okay, so now second question is, state the class of students that is most likely to proceed to qualification under this model, and that which is least likely. Okay, so this is actually a very interesting question. So what you have to see is, what is this hazard function representing here? So what do you guys think the hazard function represents here? Is the hazard qualifying a particular degree, or is the hazard not qualifying a particular degree? What do you guys think? Think about this. So what are we trying to model? So what is my hazard here? So previously throughout the whole chapter, we were looking at death as the hazard, right? Force of mortality. But what is my hazard for this particular scenario? Anyone? So maybe if you try to read the question again, it's given right up there in the question. What is the hazard?
I'm students leaving the profession before home.
Exactly right. Very good, Mihir. So the hazard is that students might leave the profession even before they qualify, right? Okay. So now if they're asking us, state the class of students that is most likely to proceed to qualification. So what do we want to see is which one of these will have the minimum hazard rate, right? So we care about the value of the hazard being minimum. And if we have a look at the hazard function that we just defined, what do we have? This baseline remains the same, but we have e raised to something. And as we know, exponential is a monotonically increasing function. So if we have a more value for this guy, then this hazard rate will be higher. So keeping that in mind, what we want to do is, we want to see which one of these will have the minimum value for the power of the exponential, right? So we have some certain betas as plus and some certain betas as minus. So what you see is to have the least possible value in the power of e, what we can do is for all the times we have a positive beta, we render those covariates to take a value of 0. And for the case where we have a negative beta, we will assign them a value of 1. And then we will see what these people are. So now I see I'm going to assign Z3 as 1 and Z5 as 1. So that if my hazard is minimum, then I know that these people are most likely to qualify, right? I hope this is making sense to you guys. Any doubts so far? So the next thing that you will do is you will have all of these covariates with their values, and you will try to see what does Z31 and Z51 represent. So Z3 is science and Z5 is UK except London, right? So for all the students who work for large employers, so again, my Z1 is 0, right? So you know that my Z1 is 0 means the person is working for a large employer and has a science degree and works in UK but outside London. So these kind of people are most likely to qualify. And for the least likely, what you will do is you will assign 1 to these positive betas and 0 to these negative betas. And for those people, we will observe a higher hazard. And if you have a higher hazard, then that means that those people are less likely to qualify. Does that make sense to you guys? Any doubts so far? Anyone? Yes or no?
No, ma'am.
Vanshita? Okay, I assume that was no. All right. So now moving on to the third part. Savri, can you read the question for me?
Yes, ma'am. A student who has been in the profession for 1 year moved from a small employer to a large employer. Express the probability that he will qualify with the large employer PL in terms of the probability that he would have qualified if he had stayed with the small employer PS, all other factors being equal.
Okay, so Mihir, can you read the question again for us? This is a very complicated question, and maybe instead of trying to read the question again, try to explain us what do you understand of this question. What are we asked to calculate? Take your time.
It is saying that the student has been the smaller employer for 1 year, and after 1 year of in that qualification, he has transferred to larger employer, right?
Yes.
So you have to calculate the probability that he will qualify as a larger employer only after the second year, given that he had stayed in the smaller year for that first year. I think. Yes.
No, that is not correct, Mihir. Try to read the question again. Do we have to figure out the exact probability? What do other people think? Savri, Vanshita, what do you guys understand of the question? This is a bit convoluted question, so try to read it and then see what is it trying to convey.
Is it like we have to express the probability PL, which is
Yes.
to qualify with a large employer in terms of like PS. Like if you would have, means we have to derive PL in terms of PS.
Exactly right. So this is what we are asked to calculate here. Mir and Savri, do you understand that? Any questions about what we are asked to do here? Savri,
Yes, ma'am, it's clear.
Mir,
Yes, ma'am.
are you sure?
I haven't actually quite understood it, but while solving, I think I'll get it.
No. We should try to understand the question first. So Vanshita, can you try to explain it to me here?
Yes, ma'am. So basically, we have to express the probability PL in terms of probability PS. So PL is the probability that we will qualify with a large employer, and PS is the probability that we would have qualified if we had stayed in the small employer.
Yeah, so basically what we are trying to see here is there is a guy who transferred from a small company to a large company, right? And then that person got qualified, let's say with the large company. So that is going to happen with some probability PL. But then we have to compare this with the probability of this person getting qualified had he stayed with the small employer itself. So we'll see where his chances are, higher of getting qualified. So we want to see whether this person getting transferred to a large employer was that helpful in terms of his being qualified or not. Maybe if that is what you want to answer by raising this particular question. So what we will do is we will now first write the probability that this person qualifies when he has transferred to a larger employer after 1 year. And we will have to compare this thing with the probability where he would have not transferred at all and stayed with this small company throughout. But again, what we know is after 1 year, this guy moved, right? So till 1 year, this guy was at the small company. So whenever we are talking about the proportion, that the very first year is not going to matter much. So what matters is what happens from the first year to the last year. So if you again read the question carefully, they specify that 3 years is what it takes for a person to qualify if they do not discontinue in the between. So now if I were to write down the probability, let's say of a person getting qualified in 3 years, that would be something like, a person not at all dropping out. So again, if you just go back to what we studied, this will be something like the occupancy probability. So what you will have here is e raised to minus integration from 1 to 3. So we are looking at what happens from first year to the third year. So 1 to 2 and then 2 to 3. And the hazard rate is something like this. So TZ and we have some DT here. So this is how we are going to represent. But again, now there is just so much to write. So I'm not going to write. And let's just go to the answer here. So if you see, this is the probability that a student who has been in the profession for 1 year will qualify, right? So we are ignoring what has happened up until 1 year because that is same for the person who transferred to a large employee after 1 year. So he was still in the small from 0 to 1 in both the cases. So now if we try to figure out PL, we will try to represent the hazard function using the model that we have just assigned, right? So we know that this guy transferred to a larger employee. So this value of Z1 will change. So if you see what you have here is no Z1. So Z1 is just 0 and the rest of these are as it is. So this is your value for PL. All right, and this e raised to stuff will get outside of the integral because they do not depend on the time variable. So this lambda 0t will vary with respect to time. And then you try to figure out the PS. So with PS, you will have 0.4 here and you know that its value is 1 because we are already assuming that this person is, staying with this small employer that he started off with. And for the rest of this stuff, we don't know the value. So we leave them as it is. And again, take all of these things outside of the integral. And as we know, we can separate this e raised to 0.4. And we again separate it outside. So this is, let me just write something. So if you have e raised to, so we have e raised to all of this stuff, right? 0.4 and something here. So what you can do is you can just write this thing as e raised to minus of all of that thing, and that thing raised to e 0.4, right? Because a raised to b raised to c is nothing but a raised to b times c. So using that, you are just rewriting this whole thing with the power of e raised to 0.4. And as we have just seen, this is nothing but PL. So you have this PS in terms of PL and vice versa, basically. So this is PL raised to e raised to 0.4. So if you see here, this is what you have as the relationship between PS and PL. And now if you see e raised to 0.4, I don't know what's the value of e raised to 0.4, but if it is greater than 1, then you would know that PS is higher than PL. And if it is less than 1, then you know that PL is higher than PS. Does this make sense to you guys? Any doubts in this? So the only trick part here would be to actually sit with the question and think, what is it that they are trying to ask you about? And once you figure that thing out, then it is very straightforward. So here we were asked to figure out the probability, but other times you might just be asked about the hazard function. So all you will have to care about is comparing this hazard function. But here they asked us to compare the probabilities, and we figured out from the question itself, which states that assuming they stay in the profession, students will qualify 3 years after joining the profession. So we know that the probability that this person will qualify in the 3 years is just e raised to minus integration of the hazard function. So I hope this is clear to you guys. Any doubts in this or anything else that we have studied? Okay, so now I will see you guys at 5 o'clock, and then we will start the next chapter. So this next chapter is actually, very nice, because we will try to see what happens about the age. So age is the only thing that we will be studying, and we will basically try to figure out the exposed to risk, the thing that comes to the denominator here, much more in depth by putting in the technicalities that we often encounter in the practical world. So I will leave the rest of the explanation for 5 o'clock. And that's it from my side for this class.